Now we need to compute a derivative of the inverse hyperbolic tangent. Now, of course, you can use the properties of the natural log to compute the derivative, but what I've tried to do here is give you extra practice with the inverse function theorem. So you choose whichever method you would like. The results will be the same for both. So what we had in the last video is that the inverse hyperbolic tangent was actually 1/2 times the natural log of 1 plus y divided by 1 minus y. Now, of course, if you like, you can move the 1/2 up and down here to the argument if you like, and when we apply the inverse function theorem, that will be much more useful to us. And so now by the inverse function theorem, the derivative of the inverse hyperbolic tangent evaluated at y is just 1 over the hyperbolic tangent derivative evaluated at x. So the idea is we've got our x up here, we're ready to go with it, but then we know that the derivative of the hyperbolic tangent is the hyperbolic secant squared. And we know this from our last video that that's just 4 over e to the x plus e to the minus x quantity squared. That's just the square of the hyperbolic cosine. Then we flip it. And so now we've got the 4 downstairs, and then of course we replace x with what's in the red box. But now of course the exponential and the natural log absorb, and we're just left with the argument. In the first case, 1 plus y divided by 1 minus y to the 1/2. And then of course the negative here will run through with the power rule and invert this fraction. So we'll get 1 minus y divided by 1 plus y to the 1/2 quantity squared. So again, the inverse function theorem works, and when we have an opportunity to use it, I think it's good for you. So now all we want to do is just square the binomial, so to speak. If we square this term, we get rid of the radical. If we square this term, we get rid of the radical. Then we multiply them together and hit it with a 2. But these are just inverses inside. So we get 2 times 1 plus y divided by 1 minus y times the inverse of that. So that's just going to end up to be 2, which is a nice simplification. So now we want a common denominator, which is 1 minus y squared if we multiply these two together. And so to get a commensurate numerator, we'll have 1 plus y squared, and we'll have a 1 minus y squared. And of course over here, since we just have a 2, we'll just put a 1 minus y squared upstairs and downstairs to rewrite the 2. Now we have a common denominator, and now hopefully we keep our fingers crossed, most everything will go away. So we expand the binomial, 1 plus y squared plus 2y, and then expand this one, 1 minus 2y plus y squared, and then of course we just get a 2 minus a 2y squared. Well, notice all the y terms absorb and all the y squared terms absorb, and the only thing that's left behind is the 1 plus 1 plus 2, which is 4, which we want to absorb also. So we have 1/4, which we already had outside, times 4 over 1 plus y squared. The 4 is absorbed, and we have our derivative right there, 1 divided by 1 minus y squared, which is a whole lot easier than the one we achieved for the inverse hyperbolic sine derivative. Now, of course, we want to be flexible. We'll let u be a differentiable function of x. Then we can actually work the derivative backwards to get an integral formula. But first, let's apply the chain rule. So the derivative of the inverse hyperbolic tangent of u will just be u prime divided by 1 minus u squared. And then, of course, this will give us an integral. The integral of du over 1 minus u squared will be the inverse hyperbolic tangent of u plus c. But now what we want to do is extend to this formula. And of course we know the natural log has a very nice property that the derivative of the natural log of the absolute value of x is just the derivative of the natural log of x. So we're going to extend to the absolute value here. And of course I have extend to the absolute value, but we still have our c here. So let me just stick that in. Okay? So we've got a nice extended formula, but of course that's not as user-friendly as we would like it to be. So what we want to do again is extend again. We're going to fix a to be positive and replace u with u divided by a. So we're just going to go into this formula and do that. So the new differential will just be 1 over a du, and then of course we replace the u. U squared becomes u squared over a squared. Okay, now we factor the 1 over a, and then when you get your common denominator and flip, you have your a squared divided by a, which gives you an a times 1 over a squared minus u squared du. Now we're not finished with this a outside yet, but just be patient. And now we go to this part. So we have 1/2 natural log, and replace u with u over a. We have 1 plus u over a divided by 1 minus u over a. Common denominator, the a's will absorb in the denominators, and we get 1/2 ln absolute value a plus u divided by a minus u. And now, of course, if you like, to make everything work out and get this a away from the integral, we divide by a. That's why I wrote the constant as the c1 here. So now when you divide by a, you get 1 over 2a, notice here, times the natural log of a plus u divided by a minus u in absolute value, and then we'll just call c1 divided by 2 the constant c. So now we have a very elegant formula here, which is also a formula that you will see when you study partial fractions. The art of doing antiderivatives is a challenging one, but you see that you will find many different ways to do the same type of integral. It just depends what you remember at the time or what you feel most comfortable with. But again, this is a very standard integral that we have actually derived via the inverse hyperbolic tangent. So again, we have a new integral formula. The integral of du over a squared minus u squared is 1 over 2a times the natural log of the absolute value of a plus u divided by a minus u plus an arbitrary constant c. And that'll be a very useful formula in your later calculus courses and of course your engineering and science courses. And we are done.